and then start your talk. So my talk today is going to be about taking away mutation with a fairly catchy subtitle. It is joint work with James, Dimi, and Ondřej. James is Ondřej's former master's student. Dimi is now a professor at Hiso Valley, if I pronounced that correctly. And Ondřej is my advisor who's still at Waterloo. And it's nice to see pictures of who you've worked for. So those are those pictures. So why am I going to talk about taking away mutation? Well, mutation is often bad because it's hard to reason about code that has it. If you're writing a build system, as you just said, well, everything touches, you have this global mutable key value store, and everything touches it, so it's hard to reason about what your build actually does. But sometimes it's actually also necessary. So here's an algorithm. It computes, probably based on the name of this algorithm, the set of prime numbers out of a list. Now, this is what some might call the sieve of Aristotles, but it's actually not. It still computes primes, but it does so inefficiently. And the reason for this is because it filters out primes. It doesn't take away the primes as you see them. It more mirrors what you might do by casting out primes. This is what the real sieve of Aristotles looks like. And you might notice that this is actually a mutable algorithm. It has many cases of mutation. It initializes a mutable array. It uses two mutable counters. And it uses this to efficiently cast away things that are composite as it sees them. It immediately discards composite numbers when they're shown to be composite, unlike the other case where, numbers are like 4 float around for a bit until you filter them out by 2. It relies on mutation, and it's really an integral part of this algorithm. You could, of course, use tail recursion and duplicating arrays to implement this functionally, but it'd be a lot messier. But this kind of also contrasts with our intuition as people who like functional programs of, well, is mutation bad? We'd like to think it's bad, but this is a use case where it's pretty good. And the answer to that, I guess, is like most things in life, there's a lot more nuance than what's on the cover. Since mutation isn't so bad in this case, because it's really just local to this function, real primes. It doesn't escape out of it. All the variables that are mutated are within it. So relative to the rest of your program, it still appears referentially transparent or pure. And this is how state's done in Haskell. Runesti and friends use this idea with the state monad to implement what might be an imperative code in Haskell, and you can actually formally show that this is safe with some really cool work that Timonish did in 2018. But that's great and all if your data structures and your variables that are mutable don't escape, but sometimes you do want them to escape. Sometimes you might want to just, instead of returning a list of primes, you might want to return a table of numbers that are true if they're prime and false if they're not. And here, you naturally just want to return the array you generate. Or if you're doing something like returning cyclic structures, you want to return the cyclic structure, but it's really hard to construct cyclic structures without mutation unless you're really well-versed in how, with laziness, and so you kind of want to have the ability to generate mutable structures that escape, but still have these nice safety properties that we just talked about. What you want, or what I say you want, is you want a mechanism for making data mutable only when you need it. And so this is what this talk is going to focus about, is how can you do so with the mechanisms in Scala that already exist to do so. So we're going to use capabilities to control setters, and I'm going to show you how this works. We're going to use singleton types to couple capabilities with our objects so it's safe, and contextual functions to make this all automatic so you don't have to write really messy code. So let's start. We're going to turn this implementation of real primes into something that's, I claim, safe, which is this, which looks exactly like what you would have written originally. So let's do this. So what's the simplest mutable structure? Okay. Come on, someone knows the answer. You look like you know the answer. It's a ref cell, right? So here's the simplest mutable structure. It's a reference cell. It has two methods, get and set. Get returns a cell value, and set lets you set it. Now, if you want to control mutation in the structure, you want to restrict how and when and where you can call set, right? And the easiest way to put additional constraints on when a function or a method can be called is just to require more arguments to it. So here we can modify set, so it takes in a second argument k called key, which you might think is, well, named that way for a reason, so that set's only called when a key is passed to it. Now, this is on our way to building something safe, but is this code right now safe? For some intuitive notion of safe. It's not, because I can counterfeit my keys and just pass them around willy-nilly, right? It's like if you had a car, if every car had the same set of keys, right? Then you can just steal your friend's nicer car. So there's a hole. So how do we fix this hole? Well, like car keys, which are tied to their cars, we want to really tie the keys that we generate to the capability, to the object that they're associated with. And we can do so with singleton types. I can create two keys. I can allocate two cells that are tied to those keys uniquely by exploiting singleton types. So here, B1's associated to K1 by tying B1 to say, well, set can only be called with an object of K1.type. And B2 is tied to K2 by, well, saying that it can only be called, set can only be called on K2.type. And then I can't counterfeit my keys. And that's good. Now, there's a bit of a flaw to this approach, which is that cell TK is kind of awkward because it's part of its public signature. Unlike, I can't really reuse this code in the setting where I had cell and T before because, well, now I've got this second type parameter. So how do we fix that? Well, Scala has support for type members. So I can just hide the capability type in the cell, making it not part of its type signature, and exploit that to have nice backward compatibility with code that reads from cells but perhaps doesn't write to it. So code like print cell, which just prints the value in a cell, it can just call c.get without worrying about what key it has, but you can't write functions like write that just write to any cell because it doesn't have the appropriate refinement or it doesn't have the appropriate knowledge of what key opens that cell. And we can also get some nice lexical-ish like scoping. So if I have a function that, makes a cell and mutates that cell within it, I can allocate a key that's hidden in that function, create that cell that's tied to that key by using the appropriate refinement. Here, type k equals k.type. Set to it when I forgot to pass in k, but that's done, and then return it. And since the key isn't escaped out of makesum, then I know that the result can't be mutated outside of makesum as well too. And I can do this automatically with some Scala support for funcs and blocks by having a helper function that just calls a func with the appropriate new key. So I can turn that into something that looks like this. I can write a immutable cell that's constructed mutably, that takes in the key that's allocated to within the scope of transiently, and set it, mutate it, when I'm done, return it, and then where it's immutable outside. And if you didn't like how key had to be passed in, because now set has this third argument, you can use Scala's contextual functions, so it appropriately selects the appropriate key out of the environment, and you can, if you didn't like how I constructed my keys by refinements, I can write a companion object that helps construct those keys with whatever ambient key is in scope at that time. So I can write code that looks like this. I create a box, a cell, I write to it, I return it, and outside of it, I can't mutate it. And that's great, right? And it looks like the code you would have written before. It looks like the code you would have written in the first place with just mutation directly. I can do one more tweak. I can just turn cell. I can turn get and set into the real getters and setters in Scala. And with that, I can just write, well, what looks like pure imperative Scala code, except with transiently to make it all look safe, and is safe-ish. And that's nice. And we can also take some of this, take these ideas, and implement them as a little bit of syntactic sugar in the Scala compiler, which is currently working on 3.5, and I have to rebase for 3.8, so that you can just use an extra keyword, and it'll all do this automatically for you. So what is this good for? Well, we did a few case studies, and I think one really cool case study is, well, here's an example of a pretty class you might have used in the Scala standard library. It's the constructor for a list cell, and we like to think it's immutable, but as a type signature indicates, as a constructor signature indicates, it's not, because next is mutable. And well, why is next mutable? Well, because we like efficiency, and we want our programs to not blow up our stack. So a lot of algorithms in the Scala standard library that operate on lists do so imperatively with imperative algorithms to avoid non-tail recursion. So here's how map's implemented. It applies a function by creating a new list iteratively and adding to that list's tail at each step. Now, the nice thing about what we just did is we can actually just take what we did in your code for list, throw in these ideas for passing around this capability attached to your case class, to the case class, and turn all these functions that work on list imperatively and show that they don't actually leak immutable lists with these capabilities that we've shown that don't escape out of the block transiently. And that's kind of cool, I think. And we can do the same thing for list buffer, which again creates lists imperatively and we can take these ideas, tie the list that the list buffer creates to a capability that doesn't escape the list buffer but is owned by it, and turn the code that imperatively deals with lists into code that safely deals with lists in the list buffer in a way that you can reason and say that the lists that the list buffer returns are immutable while letting them stay mutable within the context of the list buffer. So I think that's really cool. So what's next for us? Well, there's some cool work done by Martin and his team on capture tracking for scoping, which are capabilities right now. You can escape them if you want, ruining your safety guarantees. So it'd be nice to see how capture tracking can be used to help this, to help these ideas along by guaranteeing that these capabilities don't escape when you want, where you don't mean them to. And on that note, there's some cool work by the capture team on actually handling mutation natively within the framework, which I think Oliver and friends will be talking about sometime this week. So that's really cool. But I think there's still value for techniques like this, for lighter weight techniques, and it'd be interesting to see how they compare in real usage. And on that note, it'd be nice to see how we can integrate this into other production Scala software. And if you have any ideas, I'm all ears too. So anyways, with that said, thank you for your time. And if you have any questions, I'd love to hear them.
Great talk. Questions?
So thank you for the talk.
Thanks, Martin.
That's very interesting. So you said you can retrofit list and list buffer, which is quite impressive.
Yeah, so we retrofitted list and list buffer in the standard library, and the standard library just compiled.
Okay.
It was actually
So it's proven to be safe. Yeah.
well, it's proven to be safe. Well, you need some. Well, there's a catch there because the capabilities could escape, and we haven't integrated capture tracking to make sure they don't escape. But that's an easy fix once I rebase the library the code to 3.8.
Okay. So my question is, don't you introduce an overhead by passing these implicit parameters?
So yes, so I didn't talk about it in this talk, and you could, and there is an overhead if you implement this naively by, allocating these key objects, right?
Exactly.
But there's some cool stuff in the Scala library that allows you to pretend create objects with using erased. And the natural optimization here, which we think will work, but there's been a few bugs in the Scala compiler, either on my part or on the Scala compiler. So we haven't implemented erased to denote, make the capability or the implicits go away at runtime, but we think it's not too hard to actually stick erased there.
So erased recently got a major upgrade, and Eugene is going to talk about that later in the workshop.
Okay, that'd be great. I should talk to Eugene. Thanks for that, Martin.
Any more questions?
So, thanks for the talk. This is really interesting. You don't have to answer this. I know this is an annoying question, but at some point I was reading the Scala library's list buffer source code.
Yes.
And they have these funny memory fences in there. Does this address that in any way? Because you seem to have more semantics now, and they just seem to know they are there.
So no, when I applied this to the list buffer library, I left the fences alone because I don't know the implementation that well too. You may be able to remove it, but this is really just a safeguard for the developer, for people who write the library, so they can ensure that these lists aren't mutated where you don't expect them to, and for the end user, because they can safely know that since no one has the capability, that these lists aren't being mutated in weird ways.
Cool, thank you. That makes total sense.
Thanks for the question, Ivan.
Any more questions?
Thank you for the very interesting talk. My question is, have you thought of extending this to safe concurrency?
So the answer is no, but if you have any ideas, I'd love to hear them about this. I haven't thought, we're still kind of working out the design and where it can be applied, and because we're still looking at, the one hard thing in practice is finding Scala programs that use mutation. That's actually fairly difficult to find. So, but if you have any ideas, I'd love to hear them.
I guess a follow-up is, were you in any way inspired by Rust and like what Rust does with, this scope-based analysis?
I think we were, because we liked how Rust kind of lexically delimits scope by lifetimes and by borrowing and ownership, but we wanted to take an orthogonal note on that because we didn't. We wanted something that was a little bit more, I guess, flexible by using capabilities instead of by enforcing ownership with a linear type system. I hope that answers the question.
Okay, there's one more question.
Hi, Edward. Thanks for the talk.
Thank you for the question.
Yeah, so I was wondering, so why, I'm sure you have a good reason for this, but I was just wondering why the scoping for the key instead of creating the key when you create the class?
Why the scoping for key? So I guess with transiently here?
Yes. So usually what I would imagine is that when you create a stabilizing class as you designed it, you get a key, and now if you have two maps, you have two different keys, and so you don't mess.
Right. Okay, so why do we have? Okay, so I think this is partially because of backwards compatibility, and also because we wanted people, we wanted you to be a bit more flexible. We wanted so that you could have, you don't want to, like, I guess the annoying thing with having a single key for each object is that now you need to have a key chain of objects, of keys, right? So for simplicity, this design allows you to associate one key with multiple objects too.
Thank you.
Thank you.
Okay, thanks for the great talk. I think there are no further questions. So before we go to lunch, I have a remark. Here's a gift for you.
Oh, wow.
And
Thank you.
because you didn't get the T-shirt.
That's my fault for forgetting.
Yes. In the back of the room, you see these boxes, one of the, like this one here. And those are mugs with the Scala logo and Martin's signature. And they're up for grabs. And I'd like to ask you, if you were earlier at Scala Days and grabbed one of those there, then please leave it to others. So because we have a very tiny amount of them left, and you're welcome to take them. Otherwise, I leave you to lunch. Thank you.